Hi everyone, welcome back. We are picking up and finishing CNNs today, convolutional neural networks. Today's lecture will mark the end of what you might consider the second module or phase of this class. We've done background in terms of core fundamental theory and just fully connected neural networks. The second module was applications to computer vision with convolutional neural networks. And the third module where we'll head to is recurrent neural networks with applications to natural language processing. So that's where we're headed next. And today we're hoping to finish everything that we need from CNNs. All right, so here's our plan for today. I only added a batch norm layer on top of the convolution layer. Not quite sure why that would do that, but interesting. Interesting. Thank you for sharing. So here's the plan for today. We are trying to give you an intuition of the fully connected layers in CNNs and their interpretation as convolutions. We'll look at what we want to build towards is something called transposed convolutions, which are essential if you want to move beyond image classification to other problems. And the way we'll build that intuition is by making connections to Toeplitz matrices and expressing convolutions as matrix multiplications. Okay, so if you recall, we've been telling you that convolutional neural networks contain conv layers. We've studied them very well. They contain ReLU layers. We've studied them very well. We've studied pooling layers in between. We understand that as well. However, it's clear that conv layers also contain fully connected layers, and we just need to do, while we understand fully connected layers, we just need to handle this first transition from a convolution layer to a fully connected layer. We understand how fully connected layers interact with each other. That part's pretty clear. I think it just takes a little bit of care and concern to think about how this transition happens. And in that context, the classical way of thinking about CNNs is to divide your network into two types of layers, that at some point your CNN starts off with a tensor as an input and keeps operating convolutions on these. And at some point, it gets converted into vectors. And there is a split between convolution layers and fully connected layers. And therefore, this transition is important to understand where when that transition happens. We will challenge this view today, and you will understand that actually, you can interpret fully connected layers as a certain kind of convolution layer, so it really doesn't matter. But let's take this, let's dive into this view and try to understand it a little bit more. Okay. So the way to understand this is to think about this particular transition. So we started with some sized image, some height by width size image. It happened to be the same. We maybe resized all our images in the data set. Every time we chose a pooling layer or a strided convolution, the spatial resolution started coming down. And maybe at the very end, before we convert everything, it has come down to maybe something like a 13 by 13. It is common to go down to 13 by 13, 7 by 7, 5 by 5, or whatever. So basically, there is a small 13 by 13 by maybe something large like 512 channel dimension. So n by C1 tensor that we then have to convert into a long vector which is of size C2. So this is the first fully connected layer that takes in convolutional feature maps and converts it into vectors. And now your interpretation for this layer could be that I basically take this HL minus 1 and I convert it into a vector. So HL minus 1 vec. Right? And the way I do this is that I take all of these things. So I'm drawing 3 arrows as equivalent, and I just really string this up into a long vector. And the size of this is going to be n square C1. Right? That's the size of this vector. And it's clear why it's n square C1 because I'm just elongating a tensor. So there are n square C1 entries in this tensor, and I'm just converting that into a vector. Once I've done that, it's pretty clear how to then, after that, form a fully connected layer with C2 neurons in the next layer. Well, just connect every single thing to every single thing here. And clearly, this is going to form the weights corresponding to this neuron. There is going to be a, let me use a different color so that it's visually clear. There's going to be a weight matrix W, and that weight matrix is going to have C2 times n square C1 number of entries in that weight matrix, where the ith row in that Wi will correspond to the ith neuron here, and it'll be connected to all of these pixels. So this will be Wi. Okay. So far so good. This is just saying convert your tensor into a long vector and then shove it into a fully connected layer. Not particularly tricky. Okay. The part that does make it tricky is as soon as you operate with this understanding of this transition from convolution to fully connected layers, you realize that this locks you into a size. This fully connected layer has C2 output neurons and accepts an input vector of size C1, of size n squared C1, which means it cannot accept an input vector of size anything other than n squared C1. So if n changes, you just simply cannot perform this matrix multiplication, right? Because the matrix is of a fixed size, and if you try to perform HL equals W HL minus 1, where this vector is n tilde square C1, this matrix vector product is just not applicable, right? Can't do it. Can't perform this matrix multiplication, which means if you step back out into the architecture, we are now locked into a size, because your transition from a convolution to fully connected layer assumes that the last tensor has to have some fixed resolution, 13 by 13 by 512 or something, because this has a matrix that is expecting a vector of that many entries. So because this tensor has to be a particular size, the tensors before it have to be a particular size, so the image has to be a particular size. So if we're locked into this resolution of the image, if I had a larger image which was 640 by 480, I simply cannot get past this transition. Convolutions, by the way, accept input at test time of different sizes. Convolutions are fine, but it's this transition that's locking us into a size. Fully connected layers do not work with. And so what we're going to do, because one of the classical ways of converting an image classification problem into a detection problem is this sort of a pipeline, where we take an input image, we extract region proposals, which are bounding boxes in the image that may potentially contain an object. And then these are then cropped and warped to a fixed size that is fed into a classification CNN that says, like, here's my score for airplane, person, TV monitor, and then you ultimately make a prediction for whether this is an object or not. And so the way to convert one of the earliest ways to convert detection problems into classification problems into detection problems is to feed in crops of image. And you realize that as soon as, if your CNN is locked into a particular input size, you realize that you always have to crop and resize before forward propping. You cannot forward prop the entire image and start extracting features from some layer because you are locked into a particular size. Your CNN is locked into a particular size. So let's get around this limitation. And the way we're going to get around this limitation is by realizing, or is by making a claim that there are no fully connected layers, that all fully connected layers are actually a kind of convolution. So if we can say that these are convolutional tensors and these are also convolution tensors, that this is actually just a 1 pixel by 1 pixel by something output, and that this fully connected layer is also a convolution operation, then this is what is called a fully convolutional neural network. So this is a fully convolutional neural network because it has layers that are all expressed as convolution operations, including pooling, for example, which can be expressed as the same sliding operation. And what that means is at test time, it is not limited to a particular size, because convolutions can be run on arbitrary size. You just change the input size, the output size changes. So, for example, if this architecture was designed at training time to take 227 by 227, at test time, if I feed in 2 times the height comma width that it was designed for, all that's going to happen is that your output will become 2 times, it will become a 2 by 2 output as well. So you will just get a slightly larger output if I can express this entire network as a convolutional network. Okay, so how do we handle this transition? How do we, convert to not have to convert a tensor into a vector? Well, the answer is pretty similar to what kind of analysis we did. And the answer is instead of reshaping the input, we can reshape the output or the weights. So this right here is what we've been drawing. This is an n by c1 input coming in. Instead of stringing this into a long vector, this is the next fully connected layer, and so this is of size c2. What I will do is I will consider the ith neuron here. Let's say this is the first neuron, and I will consider all weights exiting out of this. So this is W1. The question I will ask is, W1 lives in what dimensionality? What is the size of W1 in this? And people can answer in the chat. This is an easy question. W1 has the size or dimensionality same as the input. And so what is that number that we're looking at? Come on, folks. Easy question. What is the dimensionality of W1? Which is n square C1. Thank you. N square C1. Yep. The number of entries in W1 is n square C1 because there's that many edges that go out to every single pixel here in this tensor. And so what we can do is, instead of reshaping, this is HL minus 1, instead of reshaping HL minus 1, we will reshape W1 to be the same size as the input. So I can reshape this into n by C1, and that's this entry right here. So this is the reshaped W1, and it is the same size as HL minus 1. And I can say that, this particular scalar at this scalar HL1 entry is simply HL minus 1 convolved with reshape of W1. And this is a valid convolution setting that we're doing with no padding. So if you take a n by C1 object and you perform a convolution with another n by C1 object, there is only one placement of those two tensors that is valid. And you will just place those two tensors on top of each other. You will multiply every corresponding element and you will add them together. That will give you the scalar, and then you just repeat this for every single scalar in this vector. So clearly, we can express this fully connected layer as a convolutional layer composed of these convolution filters. They are n by C1 sized filters. So it's a filter of the same size as the input coming in. And there's only one placement of those filters, and that's why we get these outputs that are really 1 pixel by 1 pixel by C2 sized outputs. So that's this tensor right here. So this is a convolution operation. It's a 1 by 1 convolution operation. I'm sorry, not a 1 by 1 convolution. It's a convolution that produces a 1 by 1 sized outputs. Does that make sense? I'll just quickly see if there are any questions about this so far. Okay. So this is a convolution, and then the fully connected layer after that similarly is also a convolution. It is a convolution that also has only one placement, and this time this convolution, the one that happens after it, this is a 1 by 1 convolution because the input is also 1 by 1, and so if the entire thing is a convolution, this is a fully convolutional network. It can run at test time on an image of any size. So you can train it on all 227 by 227 images with this particular setting of tensors expected, with this 1 by 1 output and a classification loss. But at test time, you can run it on arbitrary H by W images. And what's going to happen is that every layer just determines a downsampling factor. So the stride and pooling layers determine a spatial downsampling factor. And so if you input, if your entire network has a consequence of a certain downsampling. And so if you input something that is a multiple of 32 and you enter the right numbers, you can get a 1 by 1 output. But if you enter something larger, if you input something larger, you can get a 2 by 2 output, a 4 by 4 output, or an arbitrary H by some factor, and H by 32 and W by 32 factor output. And so then those are just spatial maps. What do you do with those spatial maps at test time? Well, you could use them for a downstream application. You could just do a spatial max pooling at test time. You could do a spatial average pooling, but they're basically just spatial probability maps telling you whether this half of or this segment of the image contains an object or not. All right, so we have so the benefits of this thinking thinking of CNNs as size-free objects at test time, at least, is that this is mathematically elegant. You realize that you can actually run CNNs at test time on arbitrary things. You don't have to think about cropping. You don't have to think about being locked into a size, and it is efficient if you want to run things on an arbitrary image without multiple crops. So the efficiency question that was being asked earlier, it doesn't change anything for training time, but if at test time you're going to start taking crops of an input image and then resize them and run them through your CNN, instead of that, now you can just run the image through the CNN, and whatever output you get, you can just take crops or subsections of that. So that's the nice way of thinking about this, and that's where efficiency comes in. Okay, so we are done with understanding fully connected layers as convolutions. Let's now start moving towards transposed convolutions, and along the way we'll meet Toeplitz matrices. Okay, so far everything that we've been doing in this class has treated like image classification as our primary problem. And one of the reasons for doing that is that it's simple. It's the simplest possible setting that we could have started with. It lets us define from a deep learning perspective all the problems that we want you to be exposed to. But really, like, that is not by any stretch of imagination the extent of problems considered by computer vision people. That's barely an entry-level problem. And for image classification, it's very clear that an entire image X goes in. There is a network and a vector of scores and scores for each classes comes out. And this lets us, this is a fairly easy way of thinking X to Y mappings. But there are many other computer vision tasks. I've just given you 3 examples here. One of them is semantic segmentation, where the goal is for every pixel in the image, label that pixel with a category corresponding to that pixel. So is this a sky pixel, a grass pixel, corresponding to an object cat, and so on. There's obviously the 2D object detection problem, where the goal is not to just say that an object is present in the image, but also output a bounding box for every instance of the object. And so, you know, there are 2 cats and a dog in this image. Apologies. I go forward, but I'm stuck. Okay, so there are two dogs and a cat in this image, and you have to output not just scores but also bounding boxes. And then there's the 3D object detection problem, where you have to output these bounding boxes that are 3D bounding boxes. So maybe your input is RGBD. So there are depth cameras that will give you a point cloud observation of the image, and your output is in a coordinate frame of the camera coordinate frame expressed in world coordinates. And you also have to output 3D bounding boxes. So you have to have some sort of depth perception of these objects. So there's many such problems. We will talk today about semantic segmentation. We will unfortunately not be able to go into details of all these other problems without, we struggle with this. We have to convert, if we have to go into all of those problems, this would get converted into a computer vision class. So let's take at least one other problem to get familiar with, and this is the semantic segmentation problem. And the semantic segmentation problem really is talking about labeling every pixel with a category. And notice that there is no notion of objects. There are just pixels. You just have to label every single. So it's almost like image classification at every pixel, if you will. And so your goal is to label every pixel in the image with a category. We do not differentiate between instances. We only care about pixels. So for example, there is cow number 1 and cow number 2 here, but all we get outputted is this, pixel level mask, where we, from the mask, cannot differentiate whether there are 2 cows here or 1 cow here. Yes, this is a poor formulation. But this is a stepping stone towards instance level recognition. So think of this as more scene understanding about what is present generally where, without delineating one instance of the object from another. Okay. So the simplest possible way of shoving everything that we've learned, or shoving this problem into everything that we've learned, is to just convert a semantic segmentation problem into like a classification problem. Basically, take a patch, decide a patch size, take all possible patches, extract that patch, feed it into a CNN, and have it output classification labels. Right? This is the simplest and the most inefficient way of doing things, because you are doing a lot of computations that are nearly identical. So if you have patch number 1 and if you have patch number 2 and they are highly overlapping, think about the convolution operations that are happening at patch number 1 and patch number 2. There is a filter here that's running over patch number 1. There's a filter here that's running over patch number 2. There are filter placements that are identical between the 2 patches. And so we are wasting a lot of computation if we do that independently, because we decided to treat every patch as a black box. And so this is extremely inefficient. We're not reusing shared features between overlapping patches. And this is just never done. You might see some versions of this idea in object detection, where you still extract windows, and maybe there are only like 100 to 500 windows in an image, and then you can do 500 forward props, but you'd never see this for semantic segmentation. Okay. The other way of doing this is to say, look, I should not treat these as independent problems. So let me try to share computation. And one of the main problems with semantic segmentation is that you need an output which is the same spatial dimension as the input. So you cannot have, one way of saying that is that, okay, I will just never lose spatial resolution. I will design a network that performs convolutions, and that will never have any stride greater than 1. It will never have any pooling layers. And so I start with a 3 by h by w. I perform some convolutions. Maybe there's a C1 number of channels here, C2 number of channels here, and so on. And maybe the channels are increasing at the last. So all my convolutions stay at the full spatial resolution. At the last convolution layer, I will convert the number of channels to be number of classes, right? I'll have that many channels. And then I will interpret at each pixel these as scores. So this is a score for category for all categories at the row comma column at this particular pixel, right? And what I will do is I can pass softmax also spatially. I can apply softmax at every pixel, and I can get probabilities. And I can define my loss as negative log predicted probability of YGT at this row comma column, and I can just sum this over all rows and columns. So basically at every pixel, I have to have a data set, and this data set contains annotated pixel level annotations of these semantic segmentations. And I will just I will use this as my loss function. So I will just sum over all these pixel values. I will have spatial softmaxes, and so I will get this sort of heat map as output, and I can just backprop through this entire thing. So this is a particular valid approach. Anybody see any problems with this approach? What sort of problems might we run into if we do this? Any guesses? So the biggest problem with this sort of an architecture is that it is computationally very slow, and in order to gain sufficient sufficient resolution to have receptor fields that are large enough, you would need to make this deep enough, and as soon as you do that, you would end up having too many parameters. So the biggest thing is convolutions at the original image resolution are extremely expensive. And you recall that the way convolutions are actually implemented is that you actually go to your input image and you take out, if you have input tensors of particular size, you have placements of those tensors of your filters. Remember that we have stride equals 1, so there's no skipping that's happening, and you basically take out all the image patches and you start putting them on rows of this matrix, and then you have a kernel matrix. These end up being extremely memory expensive, and this matrix multiplication ends up being quite slow. So if you want more details of this, there's a very nice PhD thesis by Yanqing Jia, who is the creator of Caffe among a larger team. He did a very nice analysis of an architecture called AlexNet that had come out, and he did a distribution of time analysis of GPU and CPU based forward prop. And turns out that most of the time in these neural networks are spent in the convolution layers. Like the ReLU and pooling, as you might expect, are fairly lightweight operations. They don't take long, but the convolution layers take most of the runtime. The FC layers, for example, don't take that much of a runtime of the neural network, but it's the convolution that's dominating. And this is in an architecture where the spatial resolution is being lost. If we had stuck to the original spatial resolution, we would end up paying a lot of time. And these last few have increased channel dimension. So if they also had increased spatial resolution, we would end up just spending a lot of time doing these convolutions. Okay, so how do we perform? So everybody clear on the problem definition? Somehow we have to take in, let's say, a 5 by 5 by 512 object, and we have to convert it into a 10 by 10 by some other object. So we have to gain spatial resolution, and let's see how we can do that. So one way of doing upsampling is that we can think of this as just an unpooling operation. So we can say that this is my input, which is a 2 by 2, and this is a nearest neighbor upsampling layer. So this is HL minus 1, this is HL, and what I can do is I can take at this row comma column, I can say that I'm going to go from 2 by 2 to 4 by 4 by deciding on a 2 by, for every pixel here, I'm just going to replicate that pixel 2 by 2 times. So the 0 comma, so 1 pixel gets replicated, the 2 gets replicated, the 3 gets replicated, and the 4 gets replicated. And this is what is known as nearest neighbor upsampling, because for every pixel R comma C in the output, you're finding the nearest neighbor in the, and you're just copying over values. Okay, so that's pretty easy. You could just define that as a layer. It takes in an input and it produces that as an output. This layer has no parameters, but it is obviously backproppable through, because this is just a copy operation. And so copy operations allow for gradients to flow back. You could also define things like a bed of nails operation, as it's called, where instead of placing it everywhere, you place zeros everywhere else, and there is the top left, the 0 comma 0 value is where you place this, and everything else is filled in with zeros. And typically, if you were to do this, right after upsampling, you would have a convolution layer at 4 by 4 resolution, so it's not losing resolution. That's mixing in the 0 with the 1, and so on. Okay, so those are two sort of heuristics. They have no formal justification, but we can move towards more formal methods as well. Move to the more formal method. There is another trick that is also known as max unpooling, which is the analog of max pooling. So remember max pooling operation, where in max pooling, what we did was we took a filter placement at this location, and we said this is a 2 by 2 max pooling layer with a stride of 2 as well, right? So this is a 2 by 2 max pooling where we consider a 2 by 2 window, then we shift it by another 2 by 2, and we take a max and put that entry here. So instead of just taking the max, we can also remember what the argmax was. So argmax over R comma C at every pixel. And the argmax here was the bottom right pixel. And we can design architectures. So this is an architecture where there is a symmetry in the network. So every time there was a max pooling layer, we at that same symmetric location have a max unpooling layer, And in order to perform the max unpooling, we just use this argmax value. So this is the argmax R comma C location. So at this, I should use similar colors so that it's clear, that the analog is clear. So let me just erase certain things. So this is the green box. Which one did I use? This one. This is the green box, and this is the argmax of the green box. And I can draw the red box placement. This was the argmax location, and this is the argmax, the location of the red box. So you can design architectures where there's a symmetry in your architecture. Every time there's a max pooling layer in the encoder, there's a max unpooling layer in the decoder. From the max pooling layer, you remember the argmax of the pixel. So where did this max come from? And you place the input at that argmax value. So this is just a slight generalization of the bed of nails operation. Okay. Has pixel-wise interpolation been tried with an average value filled in between pixels? Yes, sir, it has. Just wait for a slide. We will do learnt interpolation. And yes, it's been tried. So you could have fixed interpolation, or you could also have learnt interpolation. Okay, so that's where we are. We've now looked at a couple of heuristics. Now let's look at learned interpolation or learned upsampling. And these are called transposed convolutions. And now let me just clearly state that you will hear them by lots of different names. So in the literature, you will hear a term called deconvolution, which is a really, really, really bad name because deconvolution is a well understood, formally defined mathematical operation that is not what people mean when they use that term in deep learning. Deconvolution is an operation that is formally defined in signal processing. It existed, and then deep learning people came around, and it was like sort of related to that, and then they use that term, but it's not that term. It's not actual deconvolution. So if in deep learning papers you see the term deconvolution, know that what they are actually talking about are transposed convolutions, which is the formal name for this. You will also sometimes with less frequency hear terms like upconvolution, because it's a convolution-like operation whose goal is to do upsampling. You will hear terms like fractionally strided convolution, which it'll be clear once you know the operation. And backward strided convolution is also something that you'll hear very rarely. But just be aware that when you hear terms like these, what we are actually talking about are transposed convolutions. And let's use that term. That is the formal term. Please do not annoy your signal processing colleagues by calling this deconvolution. Okay, so let's learn about transposed convolutions. The way to learn about transposed convolution is that they're going to be sort of dual operations first of all, it's a process for learnable upsampling. We want to go from a 2x2 to a 4x4, and it's going to look like a dual operation to regular convolutions that you've learned. What do I mean by dual operation? Let's find out. So recall that a normal or a regular 3x3 convolution with a stride 1 and a pad 1. Let's just refresh our memory. What was convolution again? So in convolution, when you have an input and an output, remember we are going to do padding of 1, so there's zeros all around this particular input, and it's a 3x3 filter, stride 1. In a regular convolution, you place the filter W on the input, right? And there is some padding going on. Not here, obviously. And you place the filter on the input. Everywhere where there is overlap between the filter and the input, you multiply those things and you add them and you store that output in this Y 0, 0 location. So when you have to produce Y 0, 0, you place it at you place it at a particular value. You take a dot product of this input with respect to the filter, and you have that output. Stride is something that happens on the input side. So when you have to produce Y 0, 1, you slide the filter on the input side. Okay. Now it sounds like why is Dhruv repeating everything that he's just said 2 slides ago or 2 lectures ago? The reason why I'm repeating is in a couple of slides, all of these operations, stride, filter, input, output, they're going to be dualized. So I'm just trying to repeat things that you already know because in a second, it's going to all get flipped on its head. Okay. So you take a filter on the input, you slide it. Recall that when you have greater than 1 stride in a regular convolution, in output size is smaller than input size. So if you have greater than 1 stride, what happens is that you skip pixels on the input. You do not skip pixels on the output. You are still going from Y 0, 0 to Y 0, 1, and because of the stride, the Y 0, 0 and the Y 0, 1 means that you skip pixels on the input. So we are now placing from here to here. And that was so bad. We are placing this filter on the input from here to here. Okay. All right. So far, so good. So now let's meet formally or informally, pictorially, the transposed convolution. A transposed convolution also contains a filter, except in a transposed convolution, the input is typically smaller than the output. So the input is 2x2, the output is 4x4. There is still a 3x3 filter, right? There is still a number 3x3. a matrix 3 by 3, we can still have a notion of padding, we can still have a notion of stride, but the important thing is that we do not place the filter on the input, we place the filter on the output. And that seems weird. Wait, what does that mean? Why are we placing the filter on the output? Well, what we do is that we enumerate over all pixels on the input, just like we were enumerating over all pixels in the output. And for every setting of the enumeration, so in x, 0, 0, we place this W filter with this padding. So notice we've done padding underneath, in your thing with this padding. And let me just remove that for clarity. We place this at a particular place on the output. W has 9 values. Those 9 values get pasted or copied on the output. And stride greater than 1 means that when we go to x 0, we also multiply x 0, 0 here. So this red entry is x 0, 0 times W. And this blue entry is x 0, 1 times W. So basically what's happening is you're taking a pixel from the input, you're multiplying it by W, you're placing it at a particular location on the output, and then you're sliding, you're enumerating over all pixels in the input, and that corresponds to sliding on the output. So we went from x 0, 0 to x 0, 1, and so now x 0, 1 multiplied by W is placed here. Those values are put down at these locations. Anything that has an overlap just gets summed. So that is a transposed convolution operation. It is a very weird operation. I'm just placing it, I'm just introducing that operation, but then I will justify it later. So the interesting thing is stride in transposed convolution skips over pixels and output, does not skip over pixel and input. And stride in transposed convolution gives you the ratio between movement in output and movement in input, which is the dual operation as stride in regular convolution. And the way to think about this is that imagine if I had one particular example that I could give you is, imagine if I had a W which was k by k, and I chose a stride equals k. And basically what that means is I will end up constructing an output. So let's say my input was 1 by 1. If my input was 1 by 1, all that means is I will take k by k times output, and I will take my x 0, 0 times W, and I will put that here. If my input was 2 by 2, oh, that's a very ugly 2 by 2. If my input was instead much better, much more proportionate. If my input was instead 2 by 2, then I would essentially place this filter at 4 locations, and so I would end up with 2k times 2k as my output. And let me erase this part, and then that's much cleaner. Yep. So this would be x 0, 1 times W, this would be x 1, 0 times W, and so on. And so essentially the filter gets slided over by its size. And so this is a learned upsampling where we are pasting that filter times that pixel at those locations. If stride is not k, then there is some overlap, and we are also smearing in those values. Let me take a look at some questions. What about padding? How does that affect output? I'll get to that in a couple of seconds. You were padding the output and we'll get to that in a couple of seconds. What does x 0, 0 times W mean? Isn't W a 3 by 3 filter? How can we multiply it by x 0, 0? W is a 3 by 3 filter, and you can multiply a 3 by 3 filter by a scalar, which means that you multiply every entry in W. So this is like scalar times a matrix product. And the way we define a scalar times a matrix product is that you just go to every single entry in that matrix and you multiply that by that scalar. Okay. What happens at the intersections of filters? Do we just add x0, 0 w plus x0, 1 w? Yes, that is correct. That is exactly what we mean by this sum where the output overlaps. So where the blue placement and the red placement overlap, you sum those particular entries. Okay. I'll get to that padding thing question in a couple of seconds, but I just want to build some more intuition. This is what this looks like for a one-dimensional example. So you have a filter, which let's say just an input, which has just two values, A and B. This is X, this is W. This is a filter of size 3, X, Y, Z. And what we're going to do is we're going to so this is x0, this is x1. We're going to enumerate over values of x. For each value of x, we will multiply that, so it'll become ax, ay, az, and we will place it at these two locations at x, at the placement of these, and they will get summed up together. And now what padding and things are doing are basically there is zero corresponding being added here, right? That's the role of padding that we're doing. So if we do full padding, if you will get this full output. But if you don't do a padding of full, if you're just doing a padding of 1, you would get a smaller thing as output. If you don't do any padding, that you would get the least overlap as the output. But so this is what we mean by padding, and this is the example that we can see. And this is an example in 2D. So this is what I'm drawing, where what you see is this is your X input. This is your Y output, and the placement, you notice that we are enumerating over all values of X. At each of those values, we are taking this filter and we are putting it down at certain locations, and wherever there is overlap, things are getting added. I want to quickly show you a demo of this process, which is a really nice visualization from DistillPub, which is a really interesting sort of effort in constructing, rethinking publication venues. But let me show you that. Interesting. I managed to rotate it. Excellent. So this is a visualization of deconvolution and the problems with deconvolution. So let's look at a one-dimensional example. So this is the input X right here, and let me see. Yeah, this is the input X. This is the output Y. These blue things are the filter values. So our stride is deciding the size of the output. If we choose a stride of 1, then we get essentially the same size output modulo the sort of padding operation that's happening here. So if you don't pad, you will get up exactly the same output. And so this is the size of the filter. So if your filter is size 1 and you do a stride of 1, then you're basically getting identity operation, just like one-by-one convolutions implement identity operation. This is a filter of size 2. This is a filter of size 3. This is a filter of size 4, and so on. And so you can have larger and larger filters. As you introduce stride, notice what's happening is that there are holes being introduced in the input, which is just a way of visualizing the fact that you are going to skip over output values. So the fact that you're going to skip corresponds to this. So these are the valid pixels in there, and this is just another way of visualizing this. So this is a stride to size to filter, which means every pixel just gets multiplied and gets bloated up into a two-dimensional thing. And you can have larger size filters. So if you have length 4 filters with a stride of 2, then there's an overlap of 2 between these filters, and so things get added. This is that same illustration except in 2 dimensions. So this is a 3x3 filter with a stride of 2 that is just moving around and dropping those locations. and the pixel that it's looking at is coming from the input. And so you can then, of course, have cascaded layers of these things. So this is a this is a transposed convolution layer 1, where we can decide the input, the stride and the size of the filter. This is followed by another transposed convolution layer where we can decide. And notice that this is how we are gaining resolution. We first gained by a factor of 2, then we gained by another factor of 2. So what started as an input signal of size 5 gets converted into, I believe that this should be 10 and 20. So yeah, I think that's what it'll come down to. And there's a very nice, you may have already caught this, but the fact that there is overlap leads to checkerboard patterns, and that's very well known. I will stop this visualization here. So this fact that this overlap and this addition leads to a checkerboard pattern is actually a known problem with these sort of learned upsampling of methods. Right. So the things I wanted to cover in the next couple of minutes, and then I'll stop and answer questions, is that notice that the kinds of operations that you've already met can be expressed as special cases. So the nearest neighbor upsampling, I can just say that this is a transposed convolution with a particular filter of this value. So I have ones everywhere. This is my W, and nearest neighbor upsampling is just multiplying x 0, 0 with that W and placing it here, x 0, 1 placing it here, and so on. So this is a special case of transposed convolution. I can also say that this is also a special case. This is a special case with this matrix. So it has ones here and zeros everywhere else, right? So just pixels placed there, this is a special case. And as soon as you realize that these are special cases, you realize that, okay, so if these are special cases, maybe they're not optimal. Maybe we can learn a W star by minimizing, by arg-min of the loss function over all W's. So learning of upsampling can also be done just like we're learning convolution parameters, we can learn transpose convolution parameters. Okay, I wanted to get into why this operation. I don't think we'll be able to finish that because that requires viewing this as a particular kind of operation. But let me at least say why this is known as deconvolution. And so what is deconvolution for people who haven't taken signal processing classes? So formally, deconvolution, or more specifically, non-blind deconvolution, is given y, which is the output of x convolved with w, and w find x. This is the formal definition of the problem of deconvolution. That if I tell you the output of a convolution, and if I tell you what filter I convolved it with, can you recover my signal? And this is non-blind deconvolution is this operation, and there is a way of formulating convolution as matrix multiplication. We will cover that next time. You've seen some of it in the homework. And so deconvolution is asking for a matrix inverse operation. So if you can express y is equal to w times x, so if y is a one-dimensional signal, w is a matrix which is representing that filter, really what you're asking for is given w and y, find x. So invert this operation. So is there a x tilde equals w inverse of y operation that you can find? So that's what we're asking for. And we will next time show you a connection where if you write down w as a particular, as a Toeplitz matrix, then w transpose under certain assumptions can become w inverse. And w transpose equals w inverse happens when w is an orthonormal matrix. So under certain assumptions, the transpose of w is w inverse, and we'll show that that transpose is exactly implementing the transposed convolution. And transposed convolutions are called transposed convolutions because they're the transpose of the convolution matrix. And that's the connection to deconvolutions. Transposed convolutions are deconvolutions only under certain assumptions. And so this is what we'll look at next time. I will not introduce any more new material, but I'll hang around and answer questions.